Hello everyone. Today we will be studying one important theorem known as nested interval theorem. Let me write down the statement of the theorem first and then we'll try to discuss how it can be proved. Okay. So let Jn be a collection of closed and bounded intervals. Let Jn be a collection of closed and bounded intervals such that Jn plus 1 is subset of Jn for every n. Okay? Such that Jn plus 1 is subset of Jn for every n. Then intersection Jn is non-empty. That is our claim. Okay? Intersection Jn is non-empty. So what do I have? Suppose this is my J1. Then the statement says Jn plus 1 is subset of Jn. So J2 has to be something like this. J3 will be something like this. Hence we call them as nested intervals. The intervals are nested in each other. Okay. So we have to prove that the intersection of all such intervals is non-empty. So suppose J1 is A1 to B1, J2 is A2 to B2, J3 is A3 to B3 and so on. So I have AI is going in this direction. I have BI is going in this direction. So if I want to find the common region, it's going to be somewhere here. So looking at this picture, what can I say about the common region? I can say that the points in this common region have to be larger than all AIs and they have to be smaller than all BIs. Correct? So that is actually going to be the strategy of our proof. So we will try to find something which is larger than all AIs and something which is smaller than all BIs. Okay. So let A be collection of all ANs. So basically A is a collection of starting points of all intervals. Okay, so collection of left boundary points for all the intervals. Now what we know is every interval is closed and bounded. Okay. So can I say that every AN is less than or equal to every BK? At least in the picture, it looks like all the AIs are here, all the BIs are here. So every AI is smaller than every BK. But let us try to verify mathematically if this is true. So what we know is AN BN is an interval. So if AN BN is an interval, that would mean AN has to be smaller than or equal to BN. Correct? So every AN is less than or equal to the corresponding BN, that we know. So when I want to claim that AN is less than or equal to BK for every NK, I have to consider three cases. N is equal to K, N is less than K and N is greater than K. So N equal to K case has been handled here. Okay. If N is equal to K, then AN BN is an interval and AN is less than or equal to BN. Okay. Now case 2 is N is less than K. So something like I want to prove say A1 is less than B3. How do I do that? If you look at the picture, I can see that A1 is less than A3 and A3 is smaller than B3 from case 1. Correct? So we will do that. So for n less than k, what I know is, since the intervals are nested, jk is subset of jn. Correct? Of course, the statement just said jn plus 1 is subset of jn, but we know that this can be extended to jn plus 2 here, jn plus 3 here, jn minus 1 here, jn minus 2 here, and so on. So if k is larger than n, then jk is to the left. So jk is subset of jn, which means ak, bk, an, bn. This is our situation. Correct? So we will write an is smaller than or equal to ak is smaller than or equal to bk. Okay? And we wanted to prove an is smaller than or equal to bk. So that job is done. And case 3 is n is greater than k. If n is greater than k, then again from this picture what I will have? A and bn will be inside. AK, bk will be like this. So what I can write? I can write an is less than or equal to bn is less than or equal to bk. And hence an is smaller than bk. Okay. So we have proved in all three cases that an is less than or equal to bk. Okay. For every pair nk. Therefore, every bk is an upper bound for set A. And of course set A is non-empty because we have all the endpoints, left endpoints in there. Okay. Every bk is an upper bound for A. So I have A as a non-empty subset of R and A is bounded above. Okay. Therefore, by LUB property, there exists some C in R such that C is equal to LUB of A. Correct? But what I know is every bk is an upper bound. Therefore, C has to be less than or equal to bk for every k. And we said C is an upper bound for A. So, AK is less than or equal to C for every k. Therefore, AK is less than or equal to C is less than or equal to BK for every k. And therefore, C belongs to intersection JNs because C is in every interval. Hence, we have proved nested interval theorem. Okay, that is, we have proved that if I have non-empty bounded closed intervals which are nested in one another, then their intersection is also non-empty. What happens if my intervals are not closed? Suppose if I take, say, let's say for example open intervals. So if I have A and Bn's, can I say the same result is true? For example, consider intervals of the type 1 minus 1 by n to 1. Okay. First question, are they nested? So let me check. So first interval will be 1 minus 1 by 1 means 0. 1 minus 1 is 0. So I will have 0 to 1. This is my first interval. So this is my A1. This is B1. Next interval is 1 minus half to 1. So 1 minus half means half. So half, this is A2 and this is B2. then I will have 1 minus 1 by 3, that is 2 by 3. So somewhere here, so 2 by 3. So this is A3 and this same is B3. So they seem to be nested. Now the question is there a common element? Now, since the intervals are open, what if we try to take LUB, we know upper bound for this collection is actually 1 and we are stopping just before 1. So this collection turns out to be, in this intersection turns out to be actually empty. Okay. In fact, you take any point. For example, if you want to claim this is non-empty, then you will need C, which belongs to 1 minus 1 by n to 1 for every n. So that would mean that you have a C here and all 1 minus 1 by n's are here and 1 is here. So that would mean that 1 minus 1 by n is less than or equal to C for every n, which would mean 1 minus C is less than or equal to 1 by n for every n, which would mean 1 minus 1 by C is greater than or equal to n for every n. So we will actually claim that the set of natural numbers is bounded by 1 minus 1 by C, 1 by 1 minus C, which we know is contradiction to Archimedean property. Hence, this cannot be true. Okay, so this becomes false. And by contradiction, we have established that intersection of 1 minus 1 by n to 1 is phi. Now your job is to check what happens if I have intervals which are closed on one side. Okay, so A to B or A to B. And also what happens if I have unbounded intervals. So A to infinity or minus infinity to B. So check in each of these cases what happens if we take collection of intervals of this kind. Does the nested interval theorem hold or it doesn't? Okay. Let us stop here for today. Thank you.